Because that way what I avoid is having to solve the cubic equation, because I am only verifying. There might be different methods of doing this. Right? So once I choose P2, or I can choose P2 and calculate E2 from this. Because it is easier to do because we have assumed Cv to be a constant, because the equations are simplified. Right? So in that case, it's easier to do the process. So I can fix P2 and I get E2, right? And then I can substitute that into the third and the second equation, the equation of A, to verify if the equation is satisfied, then my choice of T2 and B2 are correct. Otherwise, I have to go back and do it. So you have to have a way of doing it. So let's now take up this methane. If you look at methane and look at its critical properties, Pc is 190.6 Kelvin and Pc 4.6 megapascal. So let me calculate the A and B. B is given 1/8 RPC by PC. Units are the most important. You get the units now, your whole calculation will be wrong, and I can't give any credit for that. So I can choose 8.314, that's in joule per mole. So DC has to be always given in terms of Kelvin. If it is given in terms of centigrade or whatever, you have to convert it to Kelvin, as we know, right? That's another common source of error. And then PC, what should I do? Megapascal, what does it mean to you? 4.2 into 10 power 6 actually, right? That you should know. Kilopascal means 10 power 3, right? So this is 4.2 into 10 power 6 Pascal. So what should I substitute here? Because every pressure can be given in terms of bar. Now 1 bar is how much? 10 power 5 Pascal. Newton per meter square. So Pascal is basically Newton per meter square, and that's the basic unit here. Because in joule, if you take, it is Newton meter. So everything has to go in terms of Pascal, which is Newton per meter square. Whether it's given in terms of bar or atmosphere or megapascal or kilopascal, you have to bring it everything to Pascal. Right? You should know how to do it. So PC is 4.6 into 10 power 6 Pascal. What will be the answer? Can you calculate and get the numerical answer? And tell me what units it would be in. That is important. You just give a number and your units are long, then I cannot give any credit for that. So what is the value? This is the basic, we have seen the basic elements. You should know, you should just do it correctly. These are very straightforward exercises. First point we have seen how to get the PC, BC and TC in terms of the equation of state parameters, and then the equation of state in terms of TC, BC and BC are just two of them. That's one part that's covered in the first section. Second is be able to calculate the parameters numerically correctly given the formula. Given the formula, there's a direct substitution. The units are very important. So what is the answer? 4.3 into minus 5. What units? Meter per mole. That is gram mole actually. That's very important. So you have to understand the R is 8.314. That's a bit of an inconsistency. Some books express it in terms of kilomole. So per kilomole if you want to express. So we're taking 1 in SI units. Mole is gram mole, so it's more in the CES units. But it's convenient, so most of the books write it. So this is mole, this is the same mole. You want to write it in terms of kilomole, it will actually be 10 10 power 3. You don't normally see 8.314 to 10 power 3. You just see 8.314, but if you know what units it is, the joule there is no problem, Newton meter, that will fit in perfectly. But you have to know that there is this per mole. So this will also be in per mole. That mole refers to gram, because a kilomole is 1000 times a gram. That you should understand very clear. So we express it in terms of girls. And so you can see that the V value is quite very small of the order of a liquid specific volume. So it's also important to keep in mind. Finally, so the order of 10 power minus 5 meter cube per mole. So you make a calculation and you get a huge differences. Let's say you know that you have made some mistake in the unit somewhere. You should keep in mind. If you take a look at while this law was listed, the van der Waals parameters calculated for various substances, you will see V is of the same order, around 10 power minus 5 meter cube per mole for most substances. Order, at least you should know, not the exact numbers. Now, what about A? A is 27 by 64 RTC squared by PC. So once we have figured out the problem with the units, then this is also the same. My PC I would substitute 27 by 64 and 8.314. PC very straightforward, 190.6 squared by PC again would be 4.6 into 10 power 6. And what is that? Well, the answer I have is 0.229 Newton meter power 4 by mole squared. You have to see how you are getting this A. You can easily verify this. Temperature will cancel out. You expand this out and verify that that is the units you will get. Another way of looking at it is see that P equal to RT by V minus B minus A over V squared. So we know that A must be of the same units as P times B squared. Right? That's the easiest way to guess the units for A, because it is dimensionally consistent, homogeneous. Right? So obviously the units of A has to be the same as units of P times B squared, because A by B squared should correspond to the pressure. So from that you can see P is Newton per meter squared. This is the meter cube per mole squared. So you get a meter power 6. That will cancel with the meter squared at the denominator. And mole squared also you have. So that is what it is. And again, order roughly between 0 and 1 it will be. Various substances you can see. About 0.1 to 0.6 or 7. Newton meter power 4 per mole squared. So this is an important part. That you can easily. Of course, if I had the SRK or the Ben Robinson, then I have to also, because temperature is involved. So at a particular temperature, I would have to consider this no longer be this R to B minus B. You get a temperature also, and then that will depend on whether it is evaluated at T1 or T2. So you have to get that also. Right? You have to be careful. So I am avoiding that problem by choosing the van der Waals equation of state. Right? So the first step clearly you can see is to find V1. Right? Because that is immediately can be found from the equation of state. You take that up. Another as an exercise what I will do is suppose you assume methane to be an ideal gas. Not assume, that's also one possibility. I can take methane to be behave like an ideal gas. You clearly see that at this temperature and pressure that might not be a bad approximation. We will see that. But clearly 345 bar is a much higher pressure than one order of 300. So you clearly expect. So temperature is also changing. Right? We don't know whether it's going to increase or decrease, but whatever it is, it's a huge increase in pressure. So we can no longer. But as a good first zeroth order approximation, I leave it as an because you know adiabatic reversible ideal gas constant. We take gamma that I found from YBC law. We have given a value of gamma for methane the ideal gas for methane to be something like, we have it here, 1.276. So take this as a constant, and we know that dV over gamma must be a constant. So what I will leave it as an exercise for you to find V1 and T2 very easily it can be formed an ideal gas. That will clearly give us some idea to what they expect. Right? Obviously the actual value for any other equations is going to be quite different. But you can check. So what I want you to do is to solve the source problem assuming methane to be an ideal gas and calculate V1 and V2. We discuss the results and proceed further in tomorrow's class. Are there any questions? Okay, if not, you meet tomorrow. We will run out of time.